So André-Charles Mintsa is graduated in solar energy in 2011, and then he obtained the Euro-Mediterranean Diploma on Sustainable Development. André-Charles Mintsa joined Enogia in 2013 as a project manager on different projects, such as the train energy efficiency via the heat recovery of the exhaust gases by a Rankine cycle, the installation of a ORC on solar collector in Brazil, in Greece, and in France. André-Charles is also involved as work package leader in the present H2020 European project, and also in another H2020 project named Innova Microsolar, the latter focusing on innovative microsolar heat and power system for domestic and small business buildings. So André-Charles' lecture is called ORC Technology and Implementation in Different Geological Contexts. Okay, so you can speak. You can go, André-Charles.
Perfect. Did you see my screen?
Yes.
Okay, perfect. Okay, thank you for the introduction, Christophe. Yes, I'm André-Charles. I will speak about the ORC technology and the implementation in various geological contexts. And my first question is, who know how ORC, the Organic Rankine Cycle, works? You can answer on the chat. This is my plan and my idea for this presentation. It's also speak about the Organic Rankine Cycle, but my idea is at the end of this presentation, all of you will be able to calculate and design an Organic Rankine Cycle. I know it's a little ambitious, but let's try it. This is the plan. I will make a quick introduction of what is an Organic Rankine Cycle. I will quickly speak about the story of the ORC, and after that, we'll directly work on the principle of the ORC, how to design, how to select the working fluid. I will speak a little bit about generative cycle and about an expander machine. And at the end, we will make a small exercise in order to calculate what we can produce with an Organic Rankine Cycle and geothermals. And I will speak also a little bit about heat recovery in geothermal context, about the constraint, and I will give a little word about a MIT project. Okay, just quickly, I'm working for Enogia. Enogia is a small company focused on the micro power plants to convert waste heat into electricity. I mean about waste heat, it's depending where we are, but in geothermal, it's not waste heat, but okay. We are working at the beginning on 29. We start our commercial phases in 2012. And now we got around 80 reference around the world, but not only focused on the geothermal, but on the waste heat recovery. We are also turbo machine experts. I will explain you what is a turbo machine, because it's what we use for producing electricity in Organic Rankine Cycle. And we are producing some Organic Rankine Cycle module to 1 kilowatt and 180 kilowatts. It's why we speak about micro scale power plant, because in general, on the geothermal application for heat recovery, we are speaking about megawatts. And our innovation is also a focus on low flow and low temperature. That means that we are able to produce electricity until 80 degrees Celsius. Now, a quick introduction. Organic Rankine Cycle, it's a system for waste heat recovery based on the thermodynamic cycle. The Organic Rankine Cycle, it's a variation of the water steam cycle, Carnot, but we are using outsource at low or medium temperature. Low or medium temperature can be depending of what kind of ORC you get, but you can start to produce electricity in the OTEC, Ocean Thermal Energy Conversion, at 26 degrees to for geothermal application or solar application to 200 degrees Celsius. The fluid used in this thermodynamic cycle, it's a fluid derived from organic chemistry. We can find carbon, hydrocarbon, oils, refrigerants. That's it. Okay. Quick word about the story of Organic Rankine Cycle. No. Okay. Sorry for that. Okay, better. Okay, the first person who mentioned the alternative to use an Organic Rankine Cycle is Mr. David, and 80 and 23. You mentioned it because it was looking for fluids with a low boiling temperature in order to transfer the heat from the steam to another fluids. The person who developed the cycle, really it's the Scottish engineer William John Rankine, and he developed the thermodynamic and binary cycle theory. After that, we get a few people working specifically on this technology. We got a French guy named Verda Dutremblay, who using the Organic Rankine Cycle to as an engine for a boat. And at the beginning of the 50s, we get the Israeli engineer Yusuf Broknik produced the first prototype of Organic Rankine Cycle for solar and geothermal application. And it formed the current leader of Organic Rankine Cycle in the regular market, named Ormat. I think there are a lot of installation in Kenya, in France, in Italy, about this geothermal installation on the ORC. And during the 80s, the School of Politecnico Milano go in the dance of the Organic Rankine Cycle system, and they develop a machine, an Organic Rankine Cycle with a large range of power. and he found the company named Turboden. At this time, Turboden is the European leader of the organic rankine cycle. And as Eleanor told you, the Sulz forest installation is occupied by an organic rankine cycle from Turboden. Now, okay, how does work an ORC? To know that, you need to identify each component. On the classical organic rankine cycle, we get the turbo expander, we get the condenser, it's an heat exchanger, the feed pump, and the evaporator. But to make run an organic rankine cycle, we need also a hot loop and a cold loop. The hot loop is our resource. It can be a geothermal fluid, can be oil, can be steam. This heat will go through the evaporator, the heat exchanger, and the thermal power will be transferred to the organic rankine cycle. On the organic rankine cycle, we get the pump and we get our organic rankine cycle, our refrigerants will go to the evaporator. We'll go to the evaporator and will be vaporized. Okay, then at the bottom of the ORC, we will have liquid phases, and at the top, we'll have vapor. Out of the evaporator, we'll get vapor at high pressure. We'll go through the expander. The expander will, the kinetic energy from the steam will make turn a wheel with a shaft, and we will produce electricity. And after that, we will get a steam, a vapor phase, but at low pressure. And we'll go through the condenser. And in the condenser, at the inlet, we'll get vapor at low pressure. And the working fluid will give heat, we transferred thermal heat to the cold source. And at the outlet on the condenser, we will have a liquid phases at low pressure, and we'll go back to the feed pump, and we close the loop. But to really know how it's work, an organic rankine cycle, we need to know some basic parameters: the temperature, the pressure, the mass flow on the hot loop and on the working fluids loop, and also on the cold loop. The volume flow, the specific enthalpy, the power, and the specific heat. For someone who not accustomed with thermodynamics, the enthalpy, it's the thermodynamic potential of the total energy. What is important is the difference between two steps on the cycle from calculate the enthalpy. And with the enthalpy, if you multiply the specific enthalpy by the mass flow, you will have the power. You can see now the Moliere diagram. The Moliere diagram, it's a kind of ID card for working fluids. We can have some for water, for cyclopentane, butane, or other refrigerants. The example that we took Here's the R245FA. It's quite a standard refrigerant for organic Rankine cycle. Now, on this part, you will have the pressure and the isobar. It's this line. It's a right line, then isobar. You will have the enthalpy at the bottom. You will have some curve representing the temperature. The bolt curve that you got here is the saturated curve. You got the saturated liquid curve and the saturated vapor. For the temperature, when we will touch the saturated curve, we will have the isotherm line. Because when a system changes the phases, the phases change is made at the same temperature. Okay, you will have the temperature, you will have the density on this one, and you will have the entropy. And this curve that you see is named isotropic. It's really important for the ORC design. Okay, what's happened on the ORC if we focus on this on this graphic? You will have the pressurization of the fluid at the beginning of low pressure and low temperature. You will be on the saturated liquid, and you, with the pump, you will pressurize the fluid, and you will increase the pressure on your system. And you will have a liquid phases, a saturated liquid phases at high pressure. After that, you will go through the evaporator. You will go through the evaporator. You will have some heat from the hot loop, and you will heat your fluids. At this point, you get the boiling point. It's the step when your fluid will change its phases. In this part, you will have a mixture of liquid and vapor. But when you will go, you will depace, you will reach the limit of the saturated vapor. On this part, you will get only a vapor. Why we go there? Because of the limitation of the expander. It's preferable to get a saturated vapor at the inlet of the expander in order to avoid to have some liquid in this part, because we can get some phenomenon really close to the cavitation, and it will get a real impact on your equipment lifetime. After that, we'll get the expansion. Now here we get vapor at high pressure, and we go through the expander. Expander will expand the fluids and take some useful work in order to produce electricity. And we will, as you see, the expansion follow the isotropic line. And after that, we'll go through the expander, the condenser. we will give some heat to the cold loop, and we will condensate our working fluid. But this is a theoretical part of the design of organic Rankine cycle. We got many applications for this part. We got the biogas, landfill gas application of the solar, biomass, and what it's really important for us today, the geothermal. And we got also for the energy efficiency, industrial waste heat recovery and various process, the cooling of the diesel genset, and also in the transportation. And what you need to know, it's on the organic Rankine cycle, we need only to have a temperature and a flow to produce electricity. It's quite simple like that, but we got also some constraint. Okay, some example. ORC used at biogas landfill for both jacket water and exhaust heat recovery. For the genset gas, you will burn some methane, some biogas. You will produce exhaust gas. We'll have on the old loop circulation of water. We'll go to the water jacket of the genset to cool it down, and after that we'll go through an heat exchanger, a tubular heat exchanger with on the hot part the exhaust gas and the circulation of water, and we will get around 90 degrees for the hot loop. And with this, we can produce electricity, but you need also to have a cooling device. This is the cold loop. The cold loop can be a cooling device and a dry cooler, or our refrigerants, a cooling tower. But the best one is to have a water source, I mean a river, a sea, close to the installation, because we don't need to feed the electricity for the cooling device. It's the same for generation of electricity for biomass boiler. We get the biomass, you will burn some green carburant, and we'll go through a kind of heat exchanger to take out the heat and go through the ORC in order to produce electricity again. For geothermal, it's quite the same. You will get wells with coming from a reservoir at high temperature. You will go through the ORC device, and we'll need a cooling device. But to do that, we have many options. We can have a kind of intermediate loop with a heat exchanger connected to geothermal fluids, and freshwater loop. This is can be made just in order to avoid the corrosion issue that can be a big constraint on the geothermal installation or geothermal context. It's the same for CSP, but for CSP, we are not using water. We are using a thermal oil at very high temperature, but the principle, it's quite the same. But with the CSP, because of the high temperature, we can produce electricity, but also produce hot water for end user. Now we will speak about working fluid selection. To select working fluids, we have different criteria. The main criteria are the performance, technical and economic, operating limitation, and environmental and safety criteria. What do you need to know about the working fluids? It's you can make some category. We got 3 categories of fluids. We got the dry fluids, the isotropic, and the wet. As I think you guess, the best one for ORC application is the isotropic one. What is the difference between this category? It's the slope. If you get this picture, you will have the slope on the saturated vapor. It's higher than 0. It's quite similar to, quite equal to 0, and it's less than 0. And why it is important is, as I show you on the Moliere diagram, when you will get the heating of your working fluid, you will come to saturated vapor, and you will follow the isotropic line. It's quite like that. But if you come there, you will know it will be really complicated to avoid to have some liquid on your part. And if you are there, you will need to have a more cooling to go there. It is why the best one for the working fluids, it's the isotropic one. For the technical and economic criteria, we got the price per kilogram. For the refrigerants, the price it's quite high because it's a new technology on the chemistry, and it is really important when you are designing an organic Rankine cycle. The impact could be really, really huge regarding the range of your thermal power. Bigger is the production. Biggest is the volume of the working fluid. You will need also to take in account the implementation. The implementation is the rules that we need to respect in order to manipulate your working fluid. In refrigerants, they got a lot of regulation regarding the manipulation of this one, and it could take some money to find someone able to manipulate it, and the time you get from empty your system and also feed your system. You got the operating limit criteria. It's the maximum temperature and pressure we can have on your fluids. In some fluids at high temperature, you will burn your fluids and it will lose all of is thermodynamic performance. And the other limitation is the vacuum need. I forget to told you when I presenting you the Moliere diagram, but if you get a part of air on your system, your consideration and your hypothesis will be not available, because you can have some uncompressible component on your working fluid if you put some air inside, and it will be really difficult to pressurize it and to expand it. The last criteria is the environmental and safety criteria. Is the global warming potential. We are working on the renewable energy, and the impact of our fluid on the greenhouse gases. It's really important. The global warming potential, it's a kind of comparison between the impact of your fluid and the quantity of CO2 it is equal for. You will have also the ozone depletion potential. It's a kind of coefficient that will have an impact of ozone wall. And you will have also a really important criteria. It's the fluid toxicity and flammability. It can get a huge impact on your design and of your power plant. If your fluids it's explosive or flammable, you will need to have all of your equipment ATEX, and could be get an big price on your final cost. For example, we'll take the case of working fluid selection. On the hot loop, we'll have 200 degrees. On the cold loop, we'll have 70 degrees. And the application, it's a production of heat and electricity for our house. We have 3 working fluids. We got the Novec, the cyclopentane, and the R365 MFC. Regarding the boiling temperature, it's quite similar between the cyclopentane and the 365 MFC. The critical temperature, it's quite close. It's less than the inlet on the hot loop. Could be problematic. Regarding the pressure, no problem. The superheat and everything. With the Novec, we will produce 2.4 kilowatts with an efficiency, a cycle efficiency of 10.985. The best one regarding the performance is the cyclopentane, because we'll produce around 3 kilowatts and we'll get a higher efficiency. But if you go through the environmental and for the safety, the cyclopentane, it's inflammable and toxic. It's not allowed for house for house utilization. It's quite the same for the 365. It's not environmental friendly because it gets a high global warming potential and a high atmospheric lifetime per year. And also, it's really dangerous because if you get some vapor phase, could be inflammable. Or the NOVEC, it's everything is green. The global warming potential, it's the same of the CO2. Atmospheric lifetime, it's really low, and it's not dangerous. Because at the end, the working fluid we will select for this application will be this one. Now I will speak quickly about the generative cycle. This is the first cycle I present you. When you get the turbine, the condenser, the evaporator, and the pump, and you will get the heat from the hot source, and you will give some power to the cold source. But in some case, particularly on the dry fluids, it is better to have a regenerator, because with the regenerator, we will preheat the working fluid before the evaporator. Then the evaporator will do more work. And in the same, you will at the outlet of the turbine, you will have heat, and you will use a part of this heat to heat the inlet of the evaporator. And by the way, you will cool down the outlet of the working fluid to go through the condenser. And in this consideration, the condenser will need to do more work. It can be really useful because in really high temperature, you can improve your total efficiency for 30%. Now we'll speak about the expander machine. As I explained you before, at the outlet of the evaporator, you will go to the expander machine who will expand the working fluids. We get the high pressure, and you will go to the low pressure. And the pressure ratio, it's really important for the production. You will get two families of expander, the volumetric one and the vapor turbine. Quickly, on the volumetric one, you get a screw expander, a scroll, van expander, and a piston. A screw expander is a kind of screw turn on an axis. The scroll, it's different part with pressure ratio turning and giving some rotation to the shaft. For the van expander with piston, it's a kind of a linear motion. And for the vapor turbine, and I will give more explanation for the vapor turbine, we get the radial and the axial vapor turbine. For the turbine, from the radial and axial, it's depending of the inlet. If you are perpendicular to the shaft, we get in the radial inlet flow. We'll go to the stator and go to the while will be rotate, and we will have an axial outlet flow. And for the axial turbine, the inlet will be parallel to the shaft, and we'll get the stator, name the nozzle, and the rotor will be have a rotation movement, and you will go in the axial outlet flow. On this configuration, you get the radial and the axial. What's happened on the, you will get your working fluid going on this nozzle. The working fluid will be accelerated and go to the rotor. It's a kind of wheel who will turn, and it give all of in kinetic energy for the rotor. And after that, you will have a low pressure, and the kinetic energy transmit to the wheel will make the wheel turn, and also the shaft. And if I go there, you get the this is a simplified schematic of the organic Rankine cycle turbine that we use in Enogia. It is a radial turbine. When the inlet flow come radially and the outlet coaxially, you will have the expander in the wheel, the volute, the shaft. The shaft is connected to the wheel, and when the wheel will turn, the shaft will turn, and we get the electric motor. When we will generate electricity, but the electricity at this part, it's not usable. You need to redress. You need to modify it a little bit using an inverter, and the inverter will be connected to the grid. For the lifetime, you will get also the ball bearings and a water. A water is for cooling down the electrical motor. Now we will go directly on the, I don't know if I get the time, but on the isotropic expansion. As I said, you get the heat input from the evaporator to vaporize your fluid, and you will give some heat to cooling down, and you will give also some useful work for the turbine. The theoretical cycle efficiency will be the isotropic expansion enthalpy. It's the difference between this point and this point. On the heating enthalpy, it's the difference between this point and this point. But in the real life, it's not really the same, because in the real life, we do not have an isotropic expansion. We'll have a real expansion. We'll get some losses on the expander, on the generator. It's why we will not follow the isotropic line, but we'll get a kind of curve like that. Then the useful work is less in this configuration than in the theoretical. Then for the real cycle efficiency, we will have a real expansion enthalpy on the heating enthalpy, this point and this point on this line. For the real cycle efficiency, we'll get also this formula. It's the theoretical cycle efficiency multiplied by the turbine efficiency. In the turbine efficiency, we got the isotropic efficiency, you got the mechanical efficiency and electrical efficiency. At the end, for the calculation of the turbine efficiency, we get the real expansion enthalpy on the isotropic expansion enthalpy. A quick example how to design an ORC. This is the information for the client. What you need to know to design an ORC, you don't need to get some lot of information only regarding the performance. You need the inlet temperature from the hot source, the inlet temperature for the cold source, and the available thermal power. And the hypothesis that we are using, it's the turbine efficiency of 55%, a pinch in the evaporator of 2 degrees, and a pinch of a condenser of 2 degrees. A pinch is the difference between the inlet of heat exchanger on the side, primary side, and the outlet of the secondary side, because we are in counter current. Then the different step for design the ORC is to define the boiling and condensing temperature and pressure, calculate the heating enthalpy, calculate the expansion enthalpy, define the theoretical cycle efficiency, calculate the real efficiency, and also calculate the electrical power output. I made this one, and you can see the boiling point, it's here. We'll start boiling point like 6 bar and 70 degrees. We go through the expander. After the expander, here you will get the a pinch of 2 degrees, and the condensing point is here, and with the water, the cooling part, we'll get a pinch of 3 degrees, and the enthalpy inlet, the turbine, it's this point, and the theoretical expansion enthalpy of a ORC of a turbine will be the difference between this value and this value. As you see, the detent, the theoretical expansion, then we will have a 21 kilojoule per kilograms. And the outlet on the condenser, the enthalpy, it's this point, this value, 243 kilojoule per kilograms. With this data, we'll make the difference, as I said, between this and this to have the heat enthalpy. We already have the theoretical expansion. The theoretical cycle efficiency will be, this is wrong, it is 21 on 233. We get 10% for the theoretical efficiency. We know that the turbine, this was our hypothesis, the turbine efficiency is 55%, and the real cycle efficiency must be 10% multiplied by 55%, and we get 5.5%. And what we can say is the electrical output of the ORC will be 5.5 kilowatts. I hope I'm not so it's not too boring.
No, but excuse me,
Yes.
André-Charles, if you can finish in the 5 next minutes, it could be
Okay, good.
fine.
Let's go quickly. What you need to know is for the waste heat recovery, we got 2 points. The sensible heat is the heat that we can take without change phases, and you get the latent heat. It's when on your hot loop you will get the steam and you will condensate on your evaporator. And this is the best way because you will get a huge amount of thermal power available. Just for the design of the ORC, we get the sinking diagram. What you need to know is we will get the thermal power, but we'll get some losses, kernel losses, because we need to cool down the system to make our cycle close. We'll get the enthalpy, we'll get some pressure drop, we'll lose some power. We get the recoverable enthalpy. You lose some power because the conversion of enthalpy to mechanical power, it's named the turbine losses. For the mechanical power, we'll get also some losses from the generator. It's the electrical losses. After that, we'll get the electrical output on the turbine, and we'll get also the losses regarding the power electronics. And after that, you will get what you will sell on your grid. Now, the most important part, heat recovery in geothermal context. What you need to know is there are a huge resources around the world in geothermal for heating and electricity production, but it's under exploited because of many reasons. But we can define different kind of resource. We get the low enthalpy resource. It's when the temperature it's low. It's depending on who made this characterization. But for us, the low enthalpy resource, it's when it's less than 90 degrees. The medium enthalpy, it's why we are working. It's 90 to 150, and the high enthalpy resource, it's when your temperature on your resource is higher than 150. The heat recovery in geothermal context, we get a lot of constraints. It is why it is underexploited around the world, because the geothermal power plant, it's really risky for the capital intensive, about the exploration. It's a lot of cost, drilling, a lot of cost, and the risk it's really high. It's a part why it is not really developed. But we got also some issue regarding the geothermal fluids, because in the geothermal fluids we got some kind of components that are really different between various contexts. Then you need to adapt every time your equipment for these wells. Another part is the chemical composition of geothermal fluids could be really corrosive for the machine. Then you need to find the right material to fit with your fluid, and you need to do also some maintenance. And the geothermal environment, it's also critical for design of electrical component. As you know, the electrical components are in copper, and the copper gets some reaction, a chemical reaction with hydrogen sulfate contamination. It could be really problematic to install electrical equipment on the power plant. And here you get some picture of what we done in meat. We get some experiments. We put some sample of material with different material to see their behavior with a corrosion issue in Chaunois wells. And you can see this part, it's totally dead because of the corrosion of the fluid and the non-compatibility of this material. But it's not a fatality. We can find some solution in order to deploy more ORC or more geothermal around the world. For example, regarding the economic issue, you can also operate or install some organic rankine cycle in existing facilities. It was the case in Chaunois. It was the case in France in the meat project. In Chaunois, we are using a production wells to produce electricity around 20 kilowatts. For Souls, it's the same. You get the huge ORC, but after that, we get also a small amount of thermal power that you can use for a micro turbine. And in Iceland, you get also an ORC can be installed on a facility. It was natural heating for the houses, and we connect an organic rankine cycle to produce electricity. It is also necessary to identify the most resistant and cheapest material for various wells we go. And it is also necessary to develop the small geothermal power plants, because they are got a lot of small resource at low flow and low temperature. But regarding the standard performance of the ORC, it's quite low, and it will be really difficult to get a good return and invest. But a work need to be done here, and it was the plan of a meat project.
Okay. Excuse me, André-Charles, you can try to conclude because we have to move.
Okay, this is the last conclusion. Okay, perfect. This is the conclusion. Thanks. I'm really sorry about that. It's yes. Now we know for the integration of organic rankine cycle, there need a lot of work to be done. In the first part, you need to identify the resource regarding the temperature, regarding the geothermal fluid composition. What can be done? You can make some analysis to find the right material for this specific wells, and also select it. And after that, we can integrate your result in something already exists, and you can install it and produce electricity. At this time on meat project, we got 3 ORC installed on existing facility in Chaunois on oil and gas industry, in Iceland, and in Sulsu Forest geothermal plant. I hope it was not too boring for you, and thank you very much for your attention, and really sorry for the time I took for.
So thank you, André-Charles, for your interesting talk. We have no room for question, perhaps only one, very simple. So what is the approximative cost of purchasing a typical ORC? Depending, of course, on power, but just can you give an example, please?
Bigger is it, better is the price. For 200 kilowatts, the price of a standard ORC, not a geothermal ORC, but standard ORC, will be around 200K euros.
Okay. Thank you again, André-Charles, for your talk.